Now for something rather fundamental. Section 5.4, the fundamental theorem of calculus. Okay, in this section, we finally relate definite integrals and antiderivatives. As we saw previously, we've dealt with three things. We've dealt with definite integrals, which are numbers, antiderivatives, which are functions, and indefinite integrals that are sets of functions or sets of antiderivatives. This section will tie together definite integrals, those numbers, with antiderivatives and indefinite integrals in a sense. And this is accomplished by the fundamental theorem of calculus, part 2. So we'll have a couple of parts to the fundamental theorem of calculus. The second part will be in practice the most useful. Once we have this result stated, we won't have to express integrals as limits of Riemann sums as we did in the previous section. So what we know how to integrate now is very limited to the handful of small things that we did in the previous section. Well, we're about to blow that wide open with the fundamental theorem of calculus. And in this way, evaluating integrals, definite integrals, will be quote unquote easy. But it'll be as easy as finding antiderivatives, it turns out. Maybe finding antiderivatives ain't so easy. However, a conversation to be continued in Calculus 2. Much of Calculus 2 is devoted to finding antiderivatives of functions. We call a mean value theorem, theorem 4.4, mean value theorem for a function, said that if we have a differentiable function on an interval, the average or the mean rate of change equals the instantaneous rate of change at some point. Next result is also called a mean value theorem. It's a mean value theorem for definite integrals. And what it says specifically is, if f is continuous on the interval from a to b, then at some point c in that interval, f of c equals 1 over b minus a times the interval from a to b of f of x dx. Fine. But what that means is we had defined the average value of a function, or the mean value of a function, over an interval to be 1 over b minus a, integral from a to b of f of x dx. With that taken as the definition of the average value or mean value of the function, what the mean value theorem for definite integrals says then is a continuous function attains its average value, its mean value, at some point. We also had a little drawing from some point in the past along these lines. So the idea here is the average value of a function, this function here on the interval a to b, was defined as the height of a rectangle that with base, interval a to b, would have the same area as the area contained under the curve, quote unquote area, if I happen to have to deal with negative function values. So this height was defined to be the average value of the function. And the claim in the mean value theorem for definite integrals is, hey, if the function is continuous at some point, it looks like it's this point here, c, the function takes on that average value. And it could take it on several times. That's not eliminated by the statement of the mean value theorem for definite integrals, but it says there's at least one point, which makes sense. Hey, if the function is below its average somewhere, well, it'll have to be above the average somewhere else, and by the intermediate value theorem, it'll have to take on that average value. Actually, that's kind of how the proof goes. Let's go through the proof. Not long or complicated, and it does use the intermediate value theorem. Okay, mean value theorem for definite integrals. Continuous function, we got continuity on the closed interval, implies there's a point c where f of c equals this particular value here. Well, we saw in the last section, I think it was, the max-min inequality that stated that the minimum value of a function times b minus a is less than or equal to the integral, and that's less than or equal to the maximum value of the function times b minus a. The max-min inequality, we drew some rectangles to justify that. So if we'll go through and divide that conclusion by b minus a, so instead of having the b minus a's multiplied on the left and right, we'll divide those out, and we pick up a 1 over b minus a in the middle. We get the minimum of f is less than or equal to 1 over b minus a times the integral is less than or equal to the maximum of the function. Well, you got yourself a continuous function by hypothesis. F is continuous on the interval from a to b. And here we've got some number between the minimum of that function and the maximum of that function. Well, a continuous function assumes every value between its minimum and its maximum. That's the intermediate value theorem. So, of course, the function has to take this value on at some point between a and b. That is, there's a point c at which f of c equals this particular value. Not too surprising when you see the picture, actually. Let's illustrate that. An example, 5.4.1. Okay, it says prove that if f is continuous on the interval a, b, and a doesn't equal b, and if the interval from a to b of f of x dx equals 0, then the function must be 0 at least one point in the interval from a to b, at least once in the interval, as they say. Okay, well, continuous function, the mean value theorem for definite integrals applies to continuous functions. And we know the integral has a value of 0. They told us that. So by the mean value theorem for definite integrals that we just proved, we know there's a point c where f of c equals that mean value. Since the value of the integral is 0, then that mean value is 1 over b minus a times the integral times 0. The mean value is 0. And we know there's a value c by the mean value theorem for definite integrals. There's a value c where f of c equals that average, and that average is 0. That is, there's a point c where f of c equals 0, and that's what they claimed. It's the average of the function if the integral over that interval is 0. Take 0 divided by b minus a. Of course, you get 0 out for the average, and the function must attain its average value. Okay, so we're going to see two parts of the fundamental theorem of calculus. It's really the second part that's more useful. We're going to motivate the first part kind of informally. Oh, we'll prove it formally. This is a university level math class. So I owe you time provided, I owe you proofs. So we'll motivate the fundamental theorem of calculus part 1 with an informal conversation and some graphs. Suppose function f is integrable over a finite interval I. So here's function f, lowercase f. We're going to have two functions f, lowercase f and capital F. The blue function is f of t, lowercase f. For any a in this interval, so we're looking at the interval from a to b in the picture, and any x in that interval, as long as x and a are different, we can define a new function. Capital F of x equals a definite integral from a to x of f of t dt. So that would mean, provided the function is non-negative, then I can talk areas. And if it's not non-negative, then I can talk signed areas. But for picture, let's look at one where we can talk areas. That is, let's look at a blue function, lowercase f, that's non-negative. Then what this capital F function does is it gives you the area under this curve as a function of x. So when x equals a, you ain't got any area. So what we get for capital F of a is the integral from a to a of the function, and that's 0. No area has been introduced. And then as x increases, you pick up more area under the curve. However much area you have under the curve over to this point, that's what capital F tells you. So capital F is defined in such a way that it produces this cumulative area under the curve. Well, signed area in general, but in our picture, something like that. What we want to do is get some idea of the rate of change of capital F. Suppose we consider a difference quotient for capital F. Capital F of x plus h minus capital F of x over h. I'd like to take a limit as h approaches 0, so there's no surprise that that's coming down the road. But let's see what we get in terms of a picture for this. Now, f of capital F of x plus h minus capital F of x is assigned area between lowercase f, the little blue function, and say the t-axis. I think we introduced this in terms of a t-axis. X is playing a different role here. Over the interval from x to x plus h. So capital F of x plus h would be the area under the curve over to here to x plus h. Capital F of x would be the area under the curve over to here, where the input value is x. Take the difference of those two. You'll take the total area from a to x plus h, subtract away the area from a to x, and that'll just leave you with this little sliver of area here. That's what capital F of x plus h minus capital F of x is. That's what that numerator represents. The area of this resulting rectangle can be found as approximately, it's not actually a rectangle, so here's first where the approximations come in, and here's where we're losing the rigor of a proof, but we'll take care of that in detail here in a while. This is what, x to x plus h, this is h units wide, and how tall? F of x. You want to say f of x plus h, you want to say something else? I can't really argue with that. It's an approximation. I use x and I get an approximation of this little area here. So this is imprecise. We'll make it precise. All right, so that little area is approximately h times f of x for that little rectangle is drawn there. And that's also approximately the area we were talking about before. Capital F of x plus h minus capital F of x, that's the area under the curve. Really, in this picture, it chops off that little bitty piece up there at the top, but that's small is the idea. So that area under the curve over that little subinterval there is approximately h times f of x. Height, f of x, base, h. So we're approximating the area under the curve with a rectangle. That sounds familiar from Riemann sums. All right, then if we'll take this capital f of x plus h minus capital F of x and divide it by h, then that approximately equals h f of x divided by h, and I can cancel the h's there if h is not 0. So what we're getting then is that the difference quotient approximately equals the f of x. If f is continuous, then as h approaches 0, this approximation gets better and better. So for small h values, this is good. Certainly for big h values, it's not a very good approximation at all. We want to take a limit as h approaches 0, of course. And when you take a limit as h approaches 0 of the difference quotient, then you get the derivative. So you get capital F prime of x. And we're arguing that ought to equal f of x based on this picture. So it's an informal argument. You like formal arguments, it's common. But the idea is the area changes by a little bit, and that represents a rate of change of area with respect to input values. That's when we get a change in function values over change in input values. And that's approximately a derivative. Take a limit, it is a derivative. The real approximation is this little equal sign right there. So that's where the approximation stuff came in. We're arguing when you take a limit that approximation changes to an equality. So then this function that represented areas under the curve, this capital F, remember how we defined capital F, we'll need that in the proof. That was ultimately an antiderivative. Capital F, when differentiated, gives lowercase f. So an antiderivative of lowercase f must be capital F itself. Anti-differentiate the derivative, that gives you a capital F. Capital F must be an antiderivative of f. That's how we're going to evaluate integrals using antiderivatives. That's not the fundamental theorem of calculus part 1. That's part of the story though. So right here where we saw this definite integral related to an antiderivative. That's basic to the fundamental theorem of calculus. Okay, fundamental theorem of calculus part 1 talks about the derivative properties here. Says if f is continuous on the interval from a to b, then the function capital F of x defined from a to x, integral from a to x of f of t dt like we had before, has a derivative at every point in that interval, and that derivative is lowercase f of x. This computationally we'll use a little bit. It's not as important as fundamental theorem of calculus part 2, but we're relating areas and values of integrals. See, that's the problem, is finding the value of an integral. We're relating values of integrals to functions capital F, which are antiderivatives of the integrand. That's useful. That's what we'll say more explicitly in the fundamental theorem of calculus part 2. So let's look at a proof of that. All right, there's a statement again. Okay. Remember, we had defined capital F as given here. So if we look at capital F of x plus h, the variable that goes into the function appears as the upper bound on the definite integral. So capital F of x plus h would be the integral from a to x plus h of f of t dt. Capital F of x, upper bound is x. I just copy this down here. Now we've got a difference of definite integrals. Additivity would tell you that if I take the difference of these two integrals, it produces this integral on the right, an integral from x to x plus h. Actually, additivity dealt with adding integrals together. If you consider adding these last two together, which is what you get if you took this integral to the other side, we'd have an integral from a to x of f of t, followed by an integral from x to x plus h. The fact that this integral ends where this one begins says, by additivity, that's the integral from a to x plus h, the integral from a to x plus h of the integrand, lowercase f. So that's what additivity says. Explicitly, we've rewritten it by doing some subtraction here. This is the thing we're interested in because we're interested in this difference quotient that results. So we get capital F of x plus h minus capital F of x to be explicitly this in terms of definite integrals and in terms of lowercase f, divide by h, that is multiply by 1 over h. That's the same as multiplying this thing by 1 over h because this thing is the difference of f at those two given values. So we really just want to take a limit as h approaches 0 of this. This is a difference quotient. That'll produce the derivative, and allegedly it'll produce some sort of behavior on the right-hand side as well. But the plan is to take a limit as h approaches 0 of this thing here. After all, this does equal, no approximations here, this equals the difference quotient. Okay, so we're dealing with a continuous function that was part of the hypotheses. The mean value theorem for definite integrals says there's some number c in the interval from x to x plus h, where f of c equals 1 over the length of that interval. We take x plus h minus x. That's where the h comes from. The b minus a stuff is h. Integral from a to b, f of t dt, where this is a and this is b. All right, so there's some value c that will equal the value of this integral because that's an average value of function f over the interval, over this interval, from x to x plus h. H changes, then the c parameter will have to change as well. We're actually getting some kind of function of h, which will matter in a second because we're going to take a limit. All right, c is between x and x plus h. When h changes, in particular, when h approaches 0, then this c function, c value, is going to have to approach x. As h gets little, this is an interval that runs from x to x plus h. Well, if h is really small, in particular if we take a limit as h approaches 0, this x plus h approaches x. C's stuck between them somewhere. Well, then c is going to have to approach x. Since we have a continuous function, that c value approaching x implies a limit as h approaches 0 of f of c is f of x, based on the fact that f is continuous at point x, hypotheses. All right, so let's take a limit then effectively of both sides of this equation. We'll take a limit as h approaches 0 of this. Actually, here it is. Remember, I said effectively, remember this integral represents the difference quotient, the difference, and with a 1 over h, the difference quotient. So when we take a limit as h approaches 0 of this quantity here, that's the same as taking a limit of the difference quotient, as we saw in the previous slide. Hey, limit of the difference quotient is a derivative. So this is giving us, by definition of derivative, the derivative of capital F. It is the limit of this difference quotient. We've seen the difference quotient equals this. We know that there's a point C between x and x plus h, where I can replace that integral with an f of c. So we've done that here. And we just argued the limit as h approaches 0 of f of c equals f of x by the continuity of function f. It's important that f is continuous in the fundamental theorem of calculus. And that's what we were trying to show. We were trying to show the derivative of capital F is lowercase f. That is, capital F itself is an antiderivative of lowercase f. We've used that notation before with the capital F's. Back to the notes. All right, let's do 3 exercises that illustrate that, and then we'll do the second part of the fundamental theorem of calculus. Okay, so let's illustrate what's going on here with this fundamental theorem of calculus thing. Find the derivative of y with respect to x, where y is given as this definite integral. They're taking x to be greater than 0. We don't want an integral of a continuous function. This function has a problem at 0. So that's the reason they put that hypothesis on there. Okay, f of t, the integrand 1 over t, that's a continuous function on the interval from x to 1 or 1 to x. It's continuous on both of those intervals, whether x is bigger than or less than 1. They didn't tell us that. At 0, we've got a problem, but we've stayed away from 0. So 1 over t, the integrand, is continuous on the interval with which we're dealing. So the fundamental theorem of calculus applies to say, if we differentiate this function y, that is, if we differentiate the integral from 1 to x of 1 over t dt, we simply get out f of x. We get out the integrand evaluated at x. So we get the 1 over t with a t replaced with an x. That is, dy dx is 1 over x. That happened pretty fast. Let's look at the fundamental theorem of calculus again. Part 1. Okay, so what it said was, if you differentiate with respect to x, got x down here, an integral, upper bound of x on that integral, just really interested in the upper bound. These two things are the same. You differentiate, you simply get this function with t replaced with an x. So I need an x here and here, and I'll get an x here. Mechanically, that's what the fundamental theorem of calculus part 1 says. And that's exactly what we did. We had an x at the top of the integrand. We were differentiating with respect to x. We simply took that integrand and replaced the t with an x, right? Took the integrand, replaced the t with an x, right? It went from 1 over t to 1 over x. As long as I've got x's here and here, I need the same thing there and there to use the fundamental theorem of calculus part 1. So an odd thing to do, well, they're trying to illustrate the fundamental theorem of calculus part 1. Let's do one that's a little more involved. Okay, find dy dx when y equals x times the integral from 2 to x squared sine t cubed dt. Okay, first off, you got yourself a product of functions of x here, so we'll have to use a product rule. The first function is x. The second function is this thing here. That depends on x in some way. So we have to use a product rule first off. So let's start it with that. All right, we're going to have to use a product rule. We're going to let u be that upper bound, making a substitution so that we get the upper bound in terms of something else. Let's call it u. So we're doing a type of substitution here. For now, just a symbol to represent x squared. Then what we're looking at is y is x times the integral from 2 to u, sine t cubed dt, with the understanding that u equals x squared, simply a substitution. Still got two functions of x. The first function is x itself. The second function is this thing. That's a function of x, right? Right, there's an x hidden. It's hidden inside that u, but it's still there. So we need the product rule. And to differentiate the second thing, the integral, we need the fundamental theorem of calculus, part 1. All right, so to find dy dx, differentiate y with respect to x, derivative with respect to x of, let's use this representation here, x times the integral. That'd be the derivative of the first. Derivative of x is 1 times the second, just rewrite the integral, plus the first, x, times the derivative of the second. That'd be the derivative of this thing here. Now we got a problem. We don't have the same thing that we're differentiating with respect to, x, as you have up here. That's a u. We made a substitution. That means you got a composition of functions then. And this requires the chain rule. Differentiating with respect to x in a composition where we have one function u inside another function is equivalent to differentiating with respect to u and then multiplying by the derivative of u with respect to x. So by the chain rule, I know it's a chain rule because I see a little arrow there. By the chain rule, we're differentiating this. Here's the derivative of the outer function, and inside that function is the u function. So let them multiply by du dx. Remember, we thought about the chain rule as something like this. We're trying to differentiate with respect to x. It's like the du's cancel, which I said they don't cancel because this isn't division. So that doesn't make sense. This is something else, but that's a good way to remember it. That's the reason the chain rule works in an informal sense. It's because, these things, they're not quotients, they're limits of quotients, but they act kind of like quotients sometimes. So if you think of it, if you remember this as, well, it's like the du's cancel, and then we'd be left with d dx, as we had in the previous line. So there's one way to remember the chain rule. It says what it says, and what it says is you got a composition of functions multiplied by the derivative of the inner function. The inner function is u, by the way. U is x squared, so this would be 2x. And we went through that because now we've got an integral from 2 to u, and we're differentiating with respect to u. I needed the same thing as an upper bound that we're differentiating with respect to. That's the reason we introduced the u stuff. If I had an x here and an x there, we're good to go. Man, I got a u here and a u here. You're good to go. If you'll justify with the chain rule the appropriate adjustments. Okay, so we need to do our differentiation here. We're done with that first part. We've used a chain rule part. Okay, there's the previous line from the previous page. What happens when you differentiate? All right, we got a product here. I'm just differentiating the stuff in the first pair of square brackets here. What happens when you differentiate an integral? You got the same thing there and there. Fundamental theorem of calculus part 1 says, I simply take the integrand, sine t cubed, and replace the t with this. So we get sine u cubed. Replace the t with the upper bound. That's what the fundamental theorem of calculus part 1 says. It was stated in terms of x's instead of in terms of u's, but they're dummy variables. And then over here on the right, we're still carrying along this du dx. The chain rule put it there, so let me keep up with the little arrows. All right, let's change things back into terms of x's. They gave us a function of x. We'll give them an answer in terms of x. So let's see. Here we'll take the u. Remember, u was x squared. Replace it there. Du dx. U is x squared, so its derivative is 2x. So the chain rule actually just stuck a 2x on there. Came out of the derivative of this. All right, and then let's take the u here and replace that with the x squared value. Clean this up a little bit, and there's the derivative of that function. It required product rule because there's a product of functions of x. It required the fundamental theorem of calculus, part 1, because you're differentiating an integral. And it required the chain rule because you're differentiating with respect to x, and this is a composition of functions. It's the x squared function composed with however you evaluate this integral. You may have some ideas of how you might evaluate this integral. You don't know how to do that, I don't think. If you've had an extensive amount of calculus too, you might know how to do this. It can be done using series techniques. But evaluating this integral, that's not what we were asked to do. We were asked to find some derivatives. So it's an exotic way to differentiate. Let's do another one. Find dy dx under these conditions. Okay, well, it's going to be the same situation. No product rules involved here, so I'm happier with that. There's the x's. It's not at the top. We have to get it at the top. Also, that's not simply an x, that's a 2 to the x. All right, you'll have to do some chain rule stuff. Okay, so it's really just a sequence of computations. Differentiate that, differentiate this integral. I need the function of x at the top and the constant at the bottom. Swap the order. Reversing the order of integration introduces a negative sign. It was one of the properties of definite integrals from the past. I've picked up a negative sign. I put the 1 at the bottom and the 2 to the x at the top of the integral. That requires the introduction of a negative sign. Okay, let's bring that negative sign out front. And like we did in the previous one, let's let u equal 2 to the x. So the integral from 1 to 2 to the x becomes an integral from 1 to u. You want to differentiate this function of u with respect to x? Fine. Chain rule says differentiate it with respect to u and then multiply by du dx. Chain rule, just like in the last one. Now, and I went there with the chain rule. Now we've got the same thing we're differentiating with respect to here as we have as an upper bound here. Fundamental Theorem of Calculus, Part 1, tells you how to deal with that. I just take the integrand and replace the t with a u. So we'll get cube root of the square, cube root of u. Yeah, cube root of u. The negative sign travel down from the front. Chain rules put a du dx there. All right, we need the derivative of 2 to the x with respect to x. Remember that was natural log of 2 times 2 to the x. When you differentiate exponential functions, you pick up these ugly natural log things. That's why you like differentiating the natural exponential function, because this log thing is 1 and you don't see it. But to differentiate 2 to the x, we did something like this. We've also substituted in the u equals 2 to the x. And this can be rewritten a handful of ways. I mean, here's the derivative here. Here it is written in an alternative way. So, Fundamental Theorem of Calculus, Part 1, tells you a way to differentiate definite integrals. I don't recall in my career differentiating a whole bunch of definite integrals. Really, the most useful thing is the Fundamental Theorem of Calculus, Part 2. This says, again, for a continuous function, that f be a continuous function at every point of the interval a, b, and let capital F be any antiderivative of lowercase f on that interval. Then the integral, the definite integral from a to b of f of x dx is capital F of b minus capital F of a. All right, that's good news. That means you want to evaluate a definite integral, all you need is an antiderivative. So with the Fundamental Theorem of Calculus Part 2, you're as good as at evaluating definite integrals as you are at finding antiderivatives. Some bad news, you're not very good at finding antiderivatives. At the end of Calculus 1, we'll have one little technique that we'll introduce before we're done. Probably about half of Calculus 2 is devoted to finding antiderivatives. It's devoted to integration, is how they'll state it. If you look in the index of the book, all the future sections, chapters 6 and 7, I think it is, the covers integration, which is related to finding antiderivatives. Finally, I see now, and I see it in the Fundamental Theorem of Calculus Part 2. So good news, you ain't got to go through all that Riemann sum stuff and those limits and things again, but you got to find antiderivatives. Well, We'll get better at doing anti-differentiation in Calculus 2. For now, we'll just deal with functions that you can anti-differentiate to illustrate this. Let's prove that, it being the fundamental theorem of calculus and all. Must be a big deal. So let's prove that. Actually, the proof's not too long. Okay. Let's define capital G of x to be an integral from a to x of f of t dt. We know by the fundamental theorem of calculus part 1 that that thing is an antiderivative of f. If you'll differentiate both sides with respect to x, that'll give you g prime of x on this side. Remember, that'll give you lowercase f with a t replaced with an x on that side, differentiating with respect to x. So g prime of x equals lowercase f of x, fundamental theorem of calculus part 1. So g is something you differentiate to get lowercase f. Well, that is, g is an antiderivative of lowercase f. So g is an antiderivative of lowercase f. They made a statement up here that we could use any antiderivative. Well, g is some antiderivative. If f is any antiderivative of capital F is any antiderivative of lowercase f, then you know capital F of x equals capital G of x plus k for some constant k. These two functions have the same derivative. They're antiderivatives of f, so the derivative of g is lowercase f, and the derivative of capital F is also lowercase f, and that's what we're getting at backwards by referring to antiderivatives. So these two functions, capital F and capital G, they have the same derivative, so they differ by a constant. Corollary 4.2 from somewhere in the previous chapter. So I know capital F must be of this form for some k, given the fact that capital F is an antiderivative. All right, so if we look at capital F of b minus capital F of a, that's supposed to be the value of the integral. Well, we defined, or we had the relationship, capital F of x equaled capital G of x plus k. So capital F of b is G of b plus k. Capital F of a is G of a plus k. Bracket things off here. The k's cancel. That gives you G of b minus G of a, just arithmetic. And remember how G was defined. It was an integral from a to the input value. G of x was the integral from a to x of f of t dt. So G of b is the integral from a to b of f of t dt. G of a is the integral from a to a of f of t dt. Ooh, integral from a to a, that's just 0, as we saw, as we stated as a property of definite integrals. I think we're really taking it as a definition. But the integral from a to a will always be 0, as observed earlier. So we just end up with the integral from a to b of f of t dt, and that's exactly what we claimed. The integral from a to b of f of whatever d whatever. We've got it in terms of t's because of the experience we've had with the fundamental theorem of calculus, but it's a dummy variable. I could replace these t's with x's and it would read exactly like this. So definite integrals are differences of antiderivatives. You can use any antiderivative you want. May as well choose an efficient one when we're evaluating these. Next, I think, is we'll just do several examples of these. Okay, yeah, so let's just run through a whole bunch of examples to illustrate this. This is good news. These are mechanical. Okay. Evaluate the integral from -2 to 2 of x cubed minus 2x plus 3. Nightmarish if we had to do this with Riemann sums and regular partitions and limits and all of that stuff. We could do it, but it'd take a while, especially with that cubed in there. This would be a lengthy one. But we have the fundamental theorem of calculus, part 2, that says all you need is an antiderivative of the integrand. Call the integrand lowercase f, like we've been doing. What would you differentiate to get this? Well, we had some little properties of antiderivatives. You add 1 to the exponent and divide by what you get. From last section in the previous chapter, I think it was. So Antiderivative of x cubed is x to the fourth over 4, right? Differentiate it, the 4 comes down, we'll subtract 1 from the 4, the 4's cancel, yeah, you'd be left with x cubed. Anti-differentiate 2x, get x squared, there's a negative in front. Anti-differentiate 3, get 3x. You want to add a constant on here, nobody can stop you. I could add 7 to this if I wanted to, because I can use any antiderivative. So you want to add 7, you go right ahead. You're just complicating the arithmetic. You can use any antiderivative. Let's use the easiest one. Then, fundamental theorem of calculus says, to evaluate this integral, we simply take capital F, the antiderivative, and evaluate it from -2 to 2. So the symbols here, we've run across these sporadically, mean take this upper value, plug it into the function, take this lower value, plug it into the function, and take a difference. It computes the capital F of B minus capital F of A stuff. So standard notation, the bars have always been evaluated at. This is more evaluated from here to there. It's the same bounds we had on the integral. So anyhow, plug the 2 in, plug the -2 in. Be careful with parentheses because you're taking a difference here. It'd be easy to lose negative signs. Do the arithmetic, and the value is 12. So definite integrals have an area interpretation. I'm not sure that's an entirely valid interpretation. And this one, signed area for sure. I don't know if this is a non-negative function or what, but there's the value of the definite integral. And definite integrals are awfully useful things. So much so that probably about half or more of Calculus 2 is devoted to you finding definite integrals and applications of them. So all we needed was an antiderivative. So that's a whole bunch easier than Riemann sums and limits, but that's how it was defined. Evaluate the integral from -π3 to π3 sine squared t. You know how to anti-differentiate sine squared? We had a table of antiderivatives, and I don't think that was in the table, but they've given us a hint. By the half angle formula, sine squared theta is 1 minus cosine 2 theta over 2. Half angle formula from trig or pre-calculus. All right, good thing they gave us that, because I don't know how to anti-differentiate sine squared without making this substitution. Okay, we need an antiderivative of sine squared, but I don't know how to find one. And this is the standard technique of finding one, is to change the sine squared into this stuff here. So we'll take sine squared t and write it as 1 minus cosine 2t over 2. Replace the theta with a t. So we got t as the variable in the integral. Oops. Maybe bring the 1/2 out front. That gives us a 1 minus cosine 2t. And anti-differentiate this. Find an antiderivative of this function. I can leave the 1/2 out front. Anti-differentiate 1, we get the variable. It's t. In this case, anti-differentiate cosine 2t. The antiderivative of cosine is sine. The 2 requires us to divide by 2 using the chain rule backwards in this setting. Or check it. Derivative of sine 2t would be cosine 2t times 2. It would spit out a 2 by the chain rule, which would cancel with that 2, and sure enough leave us with what we had in the previous line. Here's the table that had that spelled out explicitly. Okay, so there's an antiderivative. Then we can evaluate this integral by taking an antiderivative and evaluating it from -π3 to π3. Okay, evaluating it from -π3 to π3. I plug the π3 in, I plug the -π3 in, deal with what arises from the sine of this special angle. And it looks like it produces something of this form here, simplifying. Evaluating integrals, not too bad, if you can find antiderivatives. This one involved a trick. And that trick is to get rid of the sine squared and replace it with something you do know how to integrate. How about this one? No trig functions. Got a rational function there. I don't think we can handle rational functions in general just yet. But we can rewrite that in a very amenable way for anti-differentiation. Let's take the y cubed and divide it into each of these. Y to the 5th over y cubed is y squared. Y divided by y cubed would be y to the -2. Subtract exponents. I've got a -2 out front. So we could rewrite the given question like this. And this is just powers of the variable. I can find antiderivatives by adding 1 to the exponent and dividing by what we get. Y squared has an antiderivative of y cubed over 3. Y to the -2 will add 1 to the exponent. That'll give a -1 and divide by -1, producing negative y to the -1 as an antiderivative. Is that right? Let's differentiate negative y to the -1. The -1 will come down out front. You have two negatives, so they'll cancel each other. And you'll subtract 1 from the exponent, going from -1 to -2. You'll get positive y to the -2. Positive y to the -2. The -2 is a coefficient, and we've taken care of out front. So yeah, that's right. Let's simplify that a little bit with these negatives, maybe that negative exponent. Simplifies to this. Negative times negative gives us a positive here, and take the -1, write it as a quotient, I suppose, and plug in the bounds. Plug the -1 in first, plug the -3 in second, take a difference, simplify, 22/3. The numbers don't mean anything particular to you. We're just illustrating how to use the fundamental theorem of calculus part 2. And it's just a matter of finding antiderivatives. Find the area of the shaded region. Okay, we know definite integrals represent areas. So hopefully this is just a question involving definite integrals. We're good at definite integrals if we can find antiderivatives. And that story will stay with you throughout calculus 2. You'll be able to do definite integrals for things which you could find antiderivatives. You'll just have a bunch of more techniques then to find antiderivatives than you have now. All right, they want the area of this shaded region. Remember, a definite integral gives an area under a curve, not an area over a curve. Well, that's all right. Let's talk about those areas under the curve as follows. They've given us some sort of piecewise defined thing here, I guess. It's y equals secant squared t between -π/4 and 4. So this thing here is a secant squared function. This part over here, 1 minus t squared, it's a opening downward, concave down parabola. Well, let's find the area under the secant squared function, colored it yellow down here, and let's find the area under the 1 minus t squared function, colored it orange down here. Then we'll just take this big rectangle here. I know its width and height, and we'll subtract away the area in yellow and the area in orange, both of which we can find using definite integrals. So that's what's stated here. That gives us the area as the width, 1 plus π4, distance of 1 here plus another π4. It's right minus left if you like. It's 1 minus -π4 to measure those distances, but we get a 1 plus π4 for the width. We've got a height of 2. Okay, so that'll give the width of the rectangle. The area in yellow would be the integral from -π4 to 0, secant squared. Integral from -π4 to 0, secant squared, t dt. The area in orange would be the integral from 0 to 1 of the function 1 minus t squared. Areas under curves are given by definite integrals. All right, so we can find this if we can find an antiderivative for secant squared and an antiderivative for this. Can you find an antiderivative for secant squared? You ask yourself, what has a derivative of secant squared? And we've seen secants and tangents together in this differentiation world. The derivative of tangent is secant squared. So that one's fairly straightforward. So we'll take an antiderivative of secant squared, which is just tangent. We'll evaluate that from lower to upper bounds, -π4 to 0. Anti-differentiate this, the polynomial, so that's easy enough. T minus, add 1 to the exponent, divide, t cubed over 3 and t. Evaluate it from 0 to 1. Plug the numbers in, simplify. Any observations about this number here? Well, it's positive. It better be. It's an area. I get out something down here. If it's negative, it ain't an area. And this was a legitimate area. That was the question, was to find the area. So the answer better be positive. Previously, the numbers hadn't meant a whole lot to us. Now, is this the right value? Well, I just have to double check to figure that out. But at least it's positive. If it's negative, then I know it's wrong. So a quick check on these things to see if the answer makes any sense at all. It's positive, it makes sense. I mean, it could still be wrong. I could have done the arithmetic incorrectly, but it is positive at least. Let's do another one. Find the linearization. Okay, we're moving through the higher numbered questions now. Find the linearization of this function at x equals -1. And the function g is given in terms of a definite integral. Okay. We'll have to differentiate that function, and that'll take the fundamental theorem of calculus, part 1. Remember, linearization of a function, say g at a point A, was, this is from somewhere chapter 3, I think it was. Linearization, L of x is g of A plus g prime of A times x minus A. There's the formula from your past for linearization. So we need, we've got A equals -1 here, linearizing at x equals A at x equals -1. So we have A is -1. G of A, we can plug -1 into G and see what we get. It'll be nice. And we need the derivative, and that requires the fundamental theorem of calculus, part 1. So we'll differentiate G. G prime is the derivative with respect to x of this stuff here. Okay. How about we substitute? I need to have the same thing down here that I have up there. So let's make a substitution. Let's let u equal x squared. So this is becoming old news. We've done this several times. And then we'll use a chain rule. So we'll write this as an integral from 1 to u. We'll differentiate not with respect to x, but with respect to u. You add a chain rule, then makes you stick a du dx on. Chain rule. The derivative of the 3, that's constant. Differentiate with respect to u, the integral from 1 to u, same thing as an upper limit as we have with the variable with which we're differentiating. Secant t minus 1. Fundamental theorem of calculus part 1 says you get secant with a t replaced with a u minus 1. Secant u minus 1 is what you get from that. The chain rules still play in its role over here on the right-hand side. Du dx, u is x squared, so du dx is 2x. It's put a 2x on the side. Here it is without the little arrow. We've got secant u minus 1. U was x squared, so substitute that in. And the chain rule, put the 2x on there, and there's what we get for g prime. Little weird because it requires a fundamental theorem of calculus part 1. So there's a derivative. We still got to deal with the linearization. So we found the derivative, we were given the function, and we were given the value a. So now it's a matter of plugging stuff in there. Okay, so here's what g was. Here's what we had for the derivative from the previous slide. G of A was -1. We'll plug -1 into g. That goes in right there. There's where the x is. So we'll have an integral from 1 to -1 squared, secant t minus 1 dt. That's an integral from 1 to 1. And integrals from a to a or whatever, those are always 0. It's got the same upper and lower bound. The value of the integral is 0. We just get 3 out for g. G prime, we had that here, so we'll plug x equals -1, a equals -1 in here. We'll get 2 times -1, secant squared, -1 squared minus 1. That's -2 secant 0. Secant of 0 is 1. Secant's 1 over cosine. So we get a -2 out for that value. Then the linearization is g of a plus g prime of a times x minus a. And we found all those things. G of a, g of -1 was 3, so 3 goes there. There it is. G prime of -1 was -2, so there's a slope of -2. X minus a was -1. Produces these numbers here, simplified. There's the linearization of this function at x equals -1. Some more. Another function defined using an integral. They say, find a function f, lowercase f, satisfying this equation. Okay, what you're going to do to solve this, notice the integrand, lowercase f, is the same as the function defined using that integrand. This is actually a fairly elementary example of a thing called an integral equation. So how about we take a derivative? That's in a section on fundamental theorem of calculus where you take derivatives of things like that. So let's do that. Let's differentiate because, well, that's what this section's about. So that's my main motivation. Differentiate. Okay, so we'll differentiate f and we'll differentiate this thing here. Derivative of e squared, it's constant, that's 0. We're differentiating with the same upper bound as where you have variable here. So fundamental theorem of calculus part 1 says take the t and replace it with an x, and that's what you get for that derivative. So here we've got a function that its derivative is the function itself. The derivative, f prime of x, equals f of x itself. You know any functions that satisfy that condition? Exponential functions, e to the x's, satisfy that condition. Actually, if I take any scalar multiple of e to the x, it'll satisfy that condition. Differentiate k times e to the x, where k is a constant. What do you get? The same thing. So I suspect we're dealing with a function that's some multiple of the exponential function. We need some more information. Let's plug some numbers into this function and see what happens. You don't have a lot of latitude here because you don't know what the function f is. You don't know what the integrand is. So that's the question. All right, well, how about this? Let's plug in x equals 1. Then we'll have an integral from 1 to 1. I don't care what the integrand is. The value of the integral will be 0. So let's plug in 1. Let's take f of 1. That'll give us e squared plus an integral from 1 to 1 of f of t dt. Such an integral, put it in parentheses because I substituted, such an integral is always 0. So f of 1 is e squared. I expect this to be, and this is just hoping in some sense, based on our previous experience with derivatives, I expect this to be a multiple of the exponential function. Let's evaluate that thing at x equals 1. That'll give us k times e to the 1 and give us k times e. Okay, so we've got e squared from the function. Functions of this form produce k times e. I think we got something of this form if we'll take k equals to e. If k equals e, this will be e squared, just like that. I expect this function f to be something of this form. When I plug 1 into this one, I get e squared. When I plug 1 into this one, I get k times e. All right, take k to be e, and you'll get e squared out of this one as well. If we take k to be e, then we've got f of x is k times e to the x. It's e times e to the x, which looks a little strange. It's e to the x plus 1. Did that work? Let's try some more details. All right, so let's try this e to the x plus 1 thing again. Fundamental Theorem of Calculus, Part 2, now that I have a candidate for the integrand, would say e squared plus the integral from 1 to x of e to the t dt. Let's try it with this lowercase f of x. So that gives us e to the t plus 1. It's f of t, not f of x. So we'll have e squared plus an integral from 1 to x of e to the t plus 1 dt. You know how to find an antiderivative of this exponential function? Yeah, it's its own antiderivative. So we'll have e squared plus e to the t plus 1. There's where we're doing the anti-differentiation. This was just a constant, evaluated from 1 to x. We'll plug in the upper bound. We'll subtract, plugging in the lower bound. The integral parts in these two parentheses here. That'll give us e squared plus e to the x plus 1 minus e to the 2. It's also e squared. Hey, those cancel out. You get e to the x plus 1. Now that is f of x, like it was supposed to be. So indeed, we have f of x equals this particular integral, like we were wanting, and that works for e to the x plus 1. Does it work for anything else? That wasn't the question. Well, we found a function that satisfies these conditions. There could well be other functions that satisfy these conditions. Number 74 says, show that if k is a positive constant, then the area between the x-axis and one arch of the curve y equals sine kx is 2 over k. Area between the x-axis and one arch of the curve of a sine function, sine kx, that'd be a definite integral. Areas under curves are represented by definite integrals. Here's my rendition of a sine function, y equals sine kx. I don't know what k is, so I don't know how bad the ratio is between the x-axis and the y-axis in terms of how they're calibrated. But the graph of the sine function looks like this, and we'll have an intercept at the origin when when x is 0, we'll have sine 0 is 0. When we reach pi over k, we'll have the sine of pi inside the function, which is 0 as well. So this is a thing of interest. So if we want to find that area, and we want to find the area under one of the arches, we'll just integrate this function from here to here. That is, the area is an integral from 0 to pi over k, sine kx dx. Notice the sine function is positive on that interval. Yeah, areas under positive curves are given by integrals. I could find the area of this little piece here, but it's trickier because the function's negative over here. So this is the one to concentrate on. We need to evaluate that integral. All you need is an antiderivative of this integrand, and you know how to find that. It involves cosines. And the answer is supposed to be 2 over k. Okay, so there's the area we're interested in. Let's evaluate the definite integral from 0 to pi over k, sine kx dx. We need an antiderivative. Antiderivative of sine is negative cosine. It's got a k inside. You have to divide by k. I refer you to table 4.2, I guess entry 2, from the previous chapter, or think about it. When you differentiate this cosine kx part, derivative of cosine is negative sine kx times k by the chain rule. The negative that comes out of differentiating the cosine will cancel with that negative. The k that comes out of the chain rule will cancel with that k, and indeed you'll get this back. So that's right. Or table 4.2, entry 2. Here's an antiderivative. They had to give us something we could anti-differentiate or we get stuck. Plug in the upper bound, pi over k, plug in the lower bound, 0, simplify, and sure enough, you get 2 over k as predicted. So definite integrals represent areas. We can evaluate definite integrals using antiderivatives, fundamental theorem of calculus part 2, quite a useful thing. One more related to areas. Find the area between the x-axis and the graph of this function. Okay, well, this is going to be a little involved. They give us a picture that we'll look at, but let's go through and figure out what's going on. They want to know the area between the x-axis and this function. So I need to know whether the function's positive or negative. We need the sign of that function. All right, well, can you factor this function? X squared minus x cubed minus x squared minus 2x. I can factor an x out. Oh, and then we can factor that as x plus 1 times x minus 2. So the function factors like this. Well, this function then, it's 0 at x equals 0, at x equals negative 1, and x equals positive 2. So these 3 points here are where the function itself is 0. It's a continuous function, it's a polynomial. So let's do a sign test on the function. And you're used to this. Actually, you're used to doing sign tests on first and second derivatives and learning things about increasing, decreasingness, or concave up, concave down. Here, I just want to know positive or negative of the thing. So I'll know how to deal with the integral to find the area between the x-axis and this function. So as we've often done, we'll take a test value. We've removed the -1, the 0, and the 2. All right, so that produces these 4 intervals, removing 3 points. We'll take a test value. We're lucky I only need a fraction in one of those, -1/2, in that interval from -1 to 0. Plug it in and see if the output of the function is positive or negative. I get a negative at a point, that function's negative throughout this interval. I get a positive at a point, 5/8, its function's positive throughout this interval. So that gives me where the function itself is positive and where the function is negative. And remember, when I integrate a function that's positive, definite integrals give areas under that function. If I integrate a function that's negative, we get the negative of the area. Well, we'll just throw an extra negative sign in and fix that, because we know now where this function is positive and where it's negative. They wanted us to, restating the question, find the area of the region between the x-axis and this function for x between -1 and 2. So they're looking at this piece and this piece. The other stuff turns out not to be relevant to the question they asked. Okay, so we'll integrate, function's positive here, we'll integrate from -1 to 0, the function, it's positive. We'll integrate from 0 to 2, the negative of the function. The function itself is negative, we'll throw a negative sign in and make it positive, and that'll give the area of that part. We'll integrate from -1 to 0, the function, because the function was positive from -1 to 0. From 0 to 2, the function was negative. Well, then you integrate, you're going to get negative integrals. We'll put a negative sign in there, and that'll give you the area as desired. Remember, definite integrals give signed areas. We don't want a signed area this time. They want the whole area. And we'll have a picture of it here shortly. So I need to put a negative sign in where the function's negative, ultimately to deal with, if you like, a positive integrand and an actual area, not some negative of the area. The negative goes in because the function itself is negative. Okay, here's what we had for the function. If I leave that negative outside, then I get the same integrand here. So I get the same antiderivative. Straightforward to find an antiderivative. It's a polynomial. Evaluate from -1 to 0. Evaluate from 0 to 2. There's a negative in between. Be careful. There's a lot of moving parts flying around here. This will be a difference of these two things. This will be the difference of these two things. And those differences themselves are subtracted from each other. Right? A lot of arithmetic. And I know it goes by fast in this, but you can pause it and think through what's going on. Make sure everything is in the right place. You simplify, you get 37/12. So that's the area. It's positive, so it makes sense. Straightforward computation, a little weird with the dealing with a function that's negative. The book gives you this picture. They say what's happened here is we've integrated from -1 to 0, and we get 5/12. You integrate from 0 to 2, or actually the integral of that's going to be -8/3. Well, that area is not negative, it's positive. Did we have a 5/12 and an 8/3 in what we had? Let me go back to the previous slide. There's the 5/12 and there's the 8/3, and they're added together as they should be. So that's where the 37/12 comes from. The book gives this picture. They get the same thing. They get the area here. They've made it blue because the function is positive. The area here is 8/3. The integral of that function over this interval will be -8/3. That's why we put a negative sign in to flip it to +8/3. And that's pretty much it. There's one final comment from this section. I'll just mention about net change of a function. The net change of a function capital F over the interval AB is defined to be f of b minus f of a. It's where the function stopped minus where it started. The fundamental theorem of calculus part 2 allows us to express that net change of a function as the integral of its derivative. I'd find an antiderivative of f prime of x to evaluate this integral. What's an antiderivative of f prime? F itself. F is what I differentiate to get f prime. So this net change idea can be expressed in terms of definite integrals by the fundamental theorem of calculus part 2. So it's a happy day. We can now evaluate integrals using antiderivatives. If only we were better at finding antiderivatives. But fundamental theorem of calculus It's useful in evaluating definite integrals. It ties together definite integrals and antiderivatives. In the past, we had three things. We had antiderivatives, indefinite integrals, and definite integrals. In the past, the indefinite integrals, they were sets of antiderivatives. So that's how those two were related. Well, how do definite integrals fit into this scheme? Well, you compute definite integrals of continuous functions using antiderivatives. That's what the fundamental theorem of calculus, part 2, says. So that ties those three ideas together in this last section. All right, have a nice day. We'll do the next section here after a while, and I will see you there. Bye-bye.